Hello and welcome to Stochastic Ways. Armijo backtracking is an exact line search technique used in base gradient optimization. It helps us choose a step size that satisfies a certain conditions. The line search function is just the objective function evaluated at the new point. So if the step size is equal to 0, that means there is no movement. So the function value is simply f of x. If we take the derivative of the line search function, we get the second part of Armijo condition. Combining both give us the simplified Armijo rule. Alright, now let's plot the line search function. The step size is always positive. You can't take a negative step. The plotting starts from 0 and goes on. We add a line of sufficient decrease which sets the threshold of acceptance of the step size. Any step size that gives us a value below this line is acceptable step size. The parameter beta controls the line of sufficient decrease. In the plot, you can see the lower values of beta make the line flatter, which is more forgiving, which create a larger acceptance region of the step size. As beta increase, the line becomes steeper, making it harder to find a step size that satisfies the condition. Here is a simplified Armijo algorithm. Usually set the step size eta as 1, but for learning purposes, I set it as 2.25. The top parameter, which is the shrinking parameter of the step size, we usually set it as 0.5, and the threshold parameter beta, I set it as 0.1. In this example, the line search function is 2.56 and the threshold line is at 1.55. The condition fails because the value of the line search function is greater than the value of the threshold function. We multiply the step size by 0.5 and try again. Now we get 1 point for the line search function and we get 1.77 for the threshold. So we accept the new step size. In this gradient descent example, we have the objective function on the left and the line search function on the right. Both look similar. Typically, we don't reach the exact minimum in one step, but since this is a one-dimensional convex function, it is possible. We try, but this time we'll set the step size as 1. The function value is 2.8 and the sufficient decrease line is at 1.2. We multiply the step size by 0.5. Now the function value is 1.2 and the threshold is 3.59. The condition is satisfied, so we accept the new alpha as acceptable step size for convergence. We repeat this iteration until we reach the minimum of the function.